Hello guys, today we are going to discuss this problem, Jump Game 2. This is lead code problem number 45, and what's the problem is, let's discuss that. So we are given a array, um, and we have each element nums_i represents a max length of forward jumps. In other words, if you are at jump nums_i, you can jump nums_i plus j. Okay, so it's something like that where we have to reach the end element, and whatever element we are and whatever the value at this index is, we can make maximum jumps from there. So for example, if we are at index 0, that is 2, so we can make jump up to index 2, that is from 2 to 1, or we can make max jump up to 2 to index 1, that is 3. So 2 to 3 or either 2 to 1, this way 2 to 1 or either 2 to 3, and we have to find the minimum number of jumps to reach end. So for example, let's consider this case. What can be, um, just give me a second. Okay, so what can be the jumps to reach end? So from index 0 we can okay, let me take the indexes 1 2 3 and 4. So from index 0 we can reach to 2, and from 2 we can reach to 3, and from 3 we can reach to 4. So we'll have 3 jumps here, but from 0 we can reach to 1 as well. Then we from 1, since 3 jumps are allowed, 1 2 3, we can reach directly to 4, so 2 jumps are there, so we have to return 2 in this case. The minimum number of jumps to reach last index is 2. Jump one step from index 0 to 1 and 3 steps to last index. Okay, so there can be two approaches to this problem. So one approach will be the backtracking, but backtrack will give the time limit exceed. So let's discuss the backtrack approach first. So in backtracking, what we'll do is we'll uh, start at index 0 and we'll backtrack to all possible jumps which we can make from this present position. For example, if we are at index 0, we will jump to 2, that is from if we are index 0 here, we'll jump to position 2, which is 1. Then at position 2, what all possible jumps are possible? Only one jump possible, so we'll jump to 3. Then at index 3, what all jumps are possible? That is only one jump is possible, we'll reach 4. Now, if we are, we will come back, we'll backtrack again to 2. So when we are at 2, we have already taken up a candidate that is 0 to 2, this jump. Now we'll make jump to 3. So now from 3, what all jumps are possible? So we have 3 jumps possible, right? To 4, to 1, and to 2, right? To index 4, to index 3, and to index 2. So when we reach index 4, we found that we have reached, and we'll note the steps. So the logic says is start from index 0, jump to all possible indexes from 0, and whenever we'll reach end, we'll find that the number of jumps is smaller than uh, the noted jumps, right? So this is the code. So in this code, what we are having is start index is 0, minimum jumps is int max, and we have taken the recursive backtrack function. We have start index 0 nums, and these are the jumps. That is, we have steps or the jumps, we can say. So we will start placing all the candidates in this loop. So what I have done is we will start from index. Uh, Let me take the example. Okay, this one. So what we'll have is we'll have in recursive backtrack we'll have start index as 0, nums as the same 2, 3, 1, 1, and 4, and the steps as 0. So what we'll have is we'll start with for I equal to 2 till I is greater than 0 and minus minus I. It means that we are jumping from the present index to the last step, which to the last element which we can jump. So we are jumping till 2, and what we'll do is we'll do recursive backtrack, that is the backtrack function, and the index, that is 2 plus 0, that is start index plus I, and we'll increment the jumps or the steps. But this will have a problem because in the backtracking we might traverse some of the parts, uh, some of the functions again and again which we have already traversed. So that's why its time complexity is 2 raised to power n. Because if we have, let's suppose, n uh, elements, so we can have uh, uh, at every level of this backtrack tree, we can have n iteration. So it will be 2 raised to power n, which results in a time limit exceed. So for example, let me show you. So this is the recursive backtrack function which I have implemented using uh, this is a DP. So this is a recursive backtrack function which I have implemented, and it has some 79 cases out of 150 cases passed. So okay, so let's go back to our greedy approach. So what is greedy approach is, in greedy we try to find out uh, the max element, uh, or the best solution from the given choices. For example, if you want to reach from A to D in a graph, then there are three ways. Either we can go from A to D at cost 3, we can go from A to B at cost 1, we can go from A to C at cost 2. So greedy says that choose the local best. So the local best or the least cost is 1, so we'll choose A to B at cost 1. So how this greedy approach works here? So let us take a bigger example here. So what we have is um, this one here. So what we'll do is we'll assume that we have a ladder, and we'll find the largest ladder from the range, that is from start to end range. So for example, in this case, we'll start with the max ladder as 0 or the largest ladder as 0, jumps as 0 and end as 0. And the largest ladder will be equal to, so the largest ladder will be equal to the max of the largest ladder plus num_psi. So for example, if we start at 2 at this index, so what maximum we can jump is, we can jump up to uh, index 2, right? This 0 plus 2, so index 2. And if we are at index 2, what maximum we can jump is, we can jump till index 8, that is 2 plus 6, index plus element 8. So what we'll do is we will take the maximum ladder. So let me take this example. So we are at index 0. We found the largest ladder as 2 because the first ladder we found is 2. So we will mark our as our end as 2 here. So till 2, that is between these three indexes, whatever largest ladder we'll found it, we'll note it, and when we reach the end of the present ladder, we'll just replace and increment the jumps. That's the solution. So at index 0, we found the ladder as 2. So we have end 2 and jumps as 1. Okay, because we have climbed the ladder. At index 1, we found that we have a largest ladder of 4 because 3 plus 1 is 4. We can reach 4 and our largest ladder is 2. So until 2. So we'll note the largest ladder as 4. Still, we have not reached the end of a present ladder which will end at 2. So at index 2, we have found that we found a larger ladder of 8, that is 6 plus 2 as 8. So what we'll do now is we have reached the end of present ladder, and we need to just climb the largest ladder now. So largest ladder is 8. So we climbed at 8 and we incremented jumps to 2. Now at element I equal to 3, what is our largest ladder? Is our present ladder largest, or we found a newer larger ladder? So no, we haven't found. Our present ladder is larger. At index 4, we have a ladder of 6. So if 6 is greater than Our present ladder 8? No, it is not. At index 5, we have a ladder of 9, right? 4 plus 5 is 9. So we found a bigger ladder than our ladder. So we just node it. So our largest ladder is 9 now. Now at index 6, do we find a ladder which is larger than ours? No, it is not. At index 7, we still didn't found. So it should be 9 only. At index 8, did we find a larger ladder? Yes. So our present largest ladder was 9. We found it 10. So we take the larger ladder. So while going from step to step, if we find a bigger ladder, we pick it. That's all. Right. And whenever we reach the end of our present ladder, that is the end of this jump, end this element, we'll just replace it and we'll increment it. So that's the only solution. So what happens, what we do, what we are doing here is traverse all element, find the largest ladder, whatever the largest ladder, if it is greater than the present ladder, whatever the larger is between the present ladder and the ladder which is present at the index. And if when we have reached the end of the present ladder, just increment the jumps and take the largest ladder. So the time complexity for this will be O(n) and the space complexity is O(1). So that's the solution for this one, and it's accepted, beats 96%. Thanks a lot, guys. Have a good day.